Today we are going to do section 2.6, quadric surfaces. For some reason I like to pronounce it quatic, I don't know why. But if I say that, it means quadric, okay? Quadric surfaces. That includes things like planes, and we are going to study a bunch of surfaces called paraboloids, ellipsoids, hyperboloids. You can imagine what they might look like, even just by the sound of it. Is a parabola or ellipse in 3D, all right? And we'll see that in a second. But for now, we are going to look at the cylinder. What's a cylinder? For example, let's consider in your book, page 211, a cylinder where it's drawn by the circle x squared plus y squared equals to 9, which is a circle of radius 3. And so you draw the circle on the xy plane, and then you extend c. In c can be any value, okay? So you have a bunch of if you imagine a bunch of lines straight up parallel to the z-axis that go through the circle, then it creates a cylinder, okay? Both top above and below the xy plane. Now this cylinder is defined as this way, okay? Well, that looks like a normal cylinder, but the way the book defined it is different. Now read the definition below. A set of lines parallel to a given line. So we have a bunch of lines that's parallel, say, to the z-axis. That's fine. So you have a bunch of vertical lines, and they pass through a given curve. Okay, so you imagine a curve on the ground and a bunch of parallel lines right along it, sort of like planting trees along a given path, a windy path. Now that will create something called a cylindrical surface or cylinder. The parallel lines are called the rulings. So if you imagine a windy path where you plant straight, I don't know, not trees, but telephone poles, maybe power poles. So they're all straight up, and that creates some kind of a surface. Let's look at the next page. Okay, that's the surface that you might be able to create, although this surface is sitting sideways. But it's the same idea. You have a bunch of, imagine the curve, okay, and then the trees will span the surface. However, this thing is called a cylinder by your book. I don't remember calling it that, but it doesn't matter. And even though it doesn't look anything like a normal cylinder, but the principle is the same, is that you shoot vertical lines out of a path, okay? And all the vertical lines together make some kind of a surface similar to the way a cylinder is made, which is why it's called a cylinder here. So having said that, please do example 2.55, which is you graph these graphs, and then as part of your homework. Now 2.55 is, there's a slight problem with part B, all right? The part B, when you look at it, you notice that part B is the equation z equals to 2x squared minus y. I have it graphed here. And let's see, which is fine until you look at, now my graph looks slightly different from the book, but it is basically the same thing. The problem is the book's graph has a slight mistake, because when you look at z equal to 2x squared minus y, the first thing you should notice is that the origin is contained in the graph. So as you can see, Desmos does, you can see that the origin is in it. But in the book, the origin is most definitely not in it. Okay, if you look at your book's graph, see, the origin is out, which doesn't make any sense. The origin needs to be in this thing. So this is it's a slight mistake, not a big deal. And anyway, so please graph these things by typing it into the Desmos calculator. But at the same time, also think about what it means. For example, which way the graph should bend, and what happens when y is 0, z equals to 2x squared, and what might that look like, that sort of thing. To type it in, as I have shown earlier, you just type in the equation exactly as is in the regular Desmos graph. No, I think this is the 3D graph. Doesn't matter. The point is, you need to type it in, like z equals to 2x squared minus y, and the Desmos 3D will quickly come up with a solution for you. Next, let's look at page 214, where we are talking about something called the trace. What's a trace? A trace, when you take a plane of some kind, like this one that we just did in the example, and then cut it in a certain, slice it right across and see what the intersection looks like. For example, the slice, however, is specifically by a plane that's parallel to one of the coordinates. So it's a vertical or horizontal plane, that sort of thing. Anyway, so as an example, then if you cut it, the intersection of that graph that looks like a sine, and if you cut it just right, then the intersection will look just like the sine curve. So that's what the trace is. It's tracing along the intersection of a plane, vertical plane, with the graph you're doing. The purpose of the trace is to give you an idea of what the graph look like, because we are we see things two-dimensionally, right? So then seeing the two-dimensional representation of a three-dimensional object will give us some idea of what the object looks like. Yeah, and then anyway, so quadric surfaces are in general written by, let's look at the next page, or same page, 215. The following page, quadric surfaces, in general are represented by, as you can see the definition, first by the squares, x squared, y squared, b squared, each multiplied by some constant, and then by the cross multiples, that is xy, xz, yz, all multiplied by some constant, and finally by just x, y, z themselves, again multiplied by some constant, and at the last added to some constant, okay? And that will give you a quadric surface. Now, a quadric surface is, when a quadric surface intersects with a coordinate plane, then the trace will be a conic section, because then the trace will be only 2D, because the trace is on the plane, okay? The intersection is on the plane itself, and then we can see all the different quadric surfaces. First, an ellipsoid. An ellipsoid looks very much like an ellipse, except it has a third dimension. The ellipsoid has the formula x squared over a squared, y squared plus y squared over b squared, and z squared over c squared equals to 1. That is, that you can see is, where's my ellipsoid? Well, they didn't draw the ellipsoid. Well, whatever. What happens is they just drew the trace. To draw the trace on various coordinate planes, you let various variables equal to 0. Such as let x equal to 0, so see what the trace is on the yz plane, and so on. So you got, in the example, we got 3 traces, which helps imagining what this thing looked like. Ellipsoid looks, well, like in ellipse, except in 3 dimensions. This is the page a couple of pages later. And so please do this example as part of your homework. What example is it? Example 2.56. Next, let's look at the next page, 217, where we look at something called the elliptic paraboloid. What's so elliptic paraboloid about it? It's a parabola in some cross sections, and the vertical cross sections, and it's an ellipse in the horizontal cross sections, as you can see. The elliptical paraboloid this one has a form of x squared plus a squared over a squared plus y squared over b squared equal to z over c. And yeah, okay, so that's that. And so let's look at the next page. And we'll example 2.57. Please do that as part of your homework. That is one elliptical paraboloid that you can plot. Just do this on the computer. In Desmos, that's good enough. In Desmos 3D. Next, let's look at the bottom of 219. We're talking about hyperboloids. Hyperboloids are something that looks, in some cross sections, look like a hyperbola. Hyperboloids of one sheet can be constructed using straight lines. So let's look at that, such as this artistic object. Okay, as you can see, you can build a hyperboloid with one sheet and using a bunch of sticks, and then you sort of, I don't know, crush the middle or something, and then it bends in and becomes the hyperboloid. So this, while the surface is curved, right, it just happens that there are straight lines all through the surface, and that's the whole thing how it works out. So it's pretty nice that way. All right. So then, having said that, let's example 2.58, calculating the focus of a parabolic reflector. We have already done that in parabolas. When we were studying parabolas, we also did the 3D parabolic things without really giving it that much thought. Okay, that is, we do it the same way. 2D, 3D, the focus, you calculate it the same way. So we're going to skip that and go to the next page, page 221, where we see a summary of various quadric surfaces. First, the ellipsoid. It has equation x squared plus over a squared, y squared over b squared, z squared over c squared equal to 1 when you add them up. That is, and if a, b, c are the same, that is a sphere, all right? And the traces are such that traces in all three planes, all three directions, okay, are all ellipses for this case. Next, hyperboloid of one sheet, the one that we just talked about, the one that you can build with sticks. This one looks similar to ellipsoid, except that there is a subtraction sign in here somewhere. If it's in the z, in front of z, then the hyperboloid will stand straight up. If it's in front of some other axis, it will be you'll lie down or something. Anyway, this is the one of one sheet. Why is it in one sheet? Because some hyperboloids come in two sheets. So this one that's in one sheet is sometimes an ellipse if you cut it across the top, and then sometimes a hyperbola if you cut it on the side, not down the middle, on the side, like off a little bit. Then it becomes a hyperbola. That is, it has a top curve and a bottom curve if you cut it away from the center. Yeah, like quite a ways away. So you cut only a chunk of it. And then Anyway, so that's that. And next, hyperboloids of two sheets where you have two subtraction signs. As a result, then you have two bowls, one on top, one on bottom. And sometimes these bowls might not even look like bowls if they're really, really squashed. Because the picture that we see here is quite nice and round, right? But if the constant values A and B or C are very different, like one is 1 and one is 100 or something, then the whole thing just gets crushed and you can barely recognize it when you plot it in the 3D. But you still go by the way the formula works. That is, if there are two subtraction signs, then it is a hyperboloid of two sheets, even if it doesn't look it. Same with the others. And yeah, so there's that. And then if you cut it, then it might be an ellipse. If you cut it right where it's the middle, where there's nothing, then you get nothing, okay? And there's no intersection if you cut it right where there's nothing, right? And so in other planes, if in a vertical plane, it will be a hyperbola. Yeah. Anyway, so let's go to the next page. Elliptical cone. The cone is the cone actually looks like a cone. It happens to be, and if you cut it this way, it is the elliptical cone has a different quality, is that it equals to 0, whereas the other ones that we've done so far, they all equal to 1. Okay, when the three things equal to 0, then you got a cone. And then anyway, so, and it has one negative coefficient. Next, the elliptical paraboloid is z equals to x squared over a squared plus y squared over c squared. That's the paraboloid we talked about earlier. And and it cuts into a parabola vertically, and across it cuts into an ellipse. Next, hyperbolic paraboloid. That's you can barely see the parabola. The saddle, the horse saddle situation, where you have z equals to subtract. There's a subtraction sign here. That is make it different from the elliptical one, paraboloid. But otherwise, there are these things. Okay, there are various things, and you can identify them by putting a equation into standard form and see which one it matches, and that's the one you're going to pick. And that is example 2.59. Normally what you're going to do is, you're just going to do it. Probably complete the squares again. And it's somewhat tedious, but yeah. So please do that as part of your homework. A, B, yeah, okay. So example 2.59. So for homework of this section, on page 224, please do problems 307, 13, 15, 17, 25, 33, 37, 43, 47, 51, 53, and 55. Let's see, for 353, I wrote down the answer below because I think the book didn't present the answer. So I wrote the answer here. And anyway, so that's that. So please go do your homework. And when you come back, I want to talk about problem 355. Now that you're done with homework, let's talk about problem 355. Now you're supposed to find the intersection of two surfaces. The first surface looks like a cylinder. The second one is a sphere, right? So how do we find the intersection? We're going to do what we always did. That is, we're going to find x, y in terms of z. So then y squared equals to something. You plug it in here, and that gives you an equation with just x and z. So you isolate z, and which comes to that. That's the first parametric equation. All right, and then you plug stuff back into something y or something, and soon you get the second parametric equation. Notice there are two of them, both the plus and minus version. They both fit the equation, and then we'll plot this thing in Desmos 3D by let z be t. Okay, and then of course then x equal, you just replace t. Z with t in both x and y, and then I plot it in the Desmos calculator, and here is what I got. Here's this in Desmos 3D, and I got I think I have the Desmos 3D link below and in my course in the descriptions. So once you plot it in, you notice that, remember the answer has a plus and minus value? That's because the plus one represents only half the curve. See the blue-purple curve? That's half of it. And t goes from -2 to 2. That's because there's a square root there. See, t can't get any bigger than -2 to 2. So then the red curve is the negative version. Let's see if you can see the equations clearly. Yeah, so then you plot it in, z equal to t, and x and y equal to those values, and you plug it all in, and then you adjust the value of t. They're both -2 to 2, and if that happens, then your curve winds around nicely like that. The Desmos calculator can also move, but I didn't. Yeah, next time I'll remember to put it on the iPad or something so that you can move. But right now I didn't try to get it to move. But it's very neat because then you see a beautiful 3D graph, and you can turn and to move it around by just moving the screen with your finger like this, and see it in all kinds of directions. And that marks the end of this section.